Okay. Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. I'm Dr. Frank Summers of the Office of Public Outreach, and it's my pleasure to welcome you each and every month. When you came in, if you saw them on the tables, we have our lithographs, our pretty Hubble pictures, but they're more than just pretty pictures because on the back we describe the science behind these images and give you some of the details of what's going on, okay? If you didn't grab one on the way in, please catch one on the way out. Our speaker tonight, Greg Sloan, will be talking on ashes to ashes, dust to dust, the fate of stars like the sun. And when he scheduled this talk, he told me that, all these supernovae and neutron stars and black holes, they get all the press. But what the real action is going on is in stars like the sun, and you'll find that out tonight. Next month, we're going to have some more death for you. Katie Alatalo is going to talk on 100 ways to die in the universe, okay? I'm sure you're all going to be interested in that because, hey, if it bleeds, it leads, right? In October, Gautam Narayan will be speaking on chasing supernovae with Kepler. The Kepler satellite that was designed to find extrasolar planets actually can also be repurposed in its second mission, its K2 mission, to finding supernova out there. And in November, which I note will be on the second Tuesday because Election Day is the first Tuesday. Every other year we push it back. So November 13th, Giovanni Bruno will be speaking on exoplanet atmospheres, studying the atmospheres of planets around other stars. And this is it's one of the coolest ideas we have. We actually can study the atmospheres of other planets, okay? Details are on our website. Take your favorite search engine and put in Hubble Public Talks or Space Telescope Public Lecture Series, and you'll find this page where we have our upcoming lectures on the right side, our links to watching it on either live when it is live, or the past lectures all the way back to 2005. So lots and lots of astronomy on our page. You can also sign up for our announcement email list. The announcements, if you don't like signing up on the website, just give me your email address and I'll make sure you are added to the list. If you have comments or questions, you can send email to publiclecture@stsci.edu. You can also follow us on social media. We have social media channels for Hubble, for Webb, and for the Institute on Facebook, Twitter, YouTube, and Instagram. I do a tiny amount of social media on Facebook, Google+, and Twitter, but don't expect me to be jumping on there every day. Sometimes I don't get on there for a week or two. Anyways. Unfortunately, if you looked at the clouds on your way in, you said, hey, there's a lot of them. And that means you can't use the observatory tonight. So I talked to the Maryland Space Grant folks, and they said, sorry, they're not going to open the observatory tonight. It's been a while since we've actually had good weather on these public lecture series. Hopefully that will change next month. But you don't have to wait for this. You can go to their webpage, md.spacegrant.org, and every Friday night they also do look to open it. So if you check their webpage on Fridays, they will tell you whether or not they're opening it on Fridays. Now is a really good time to look at it because there are several planets that are nice, big, and bright in the sky, and I'll tell you about them in just a second. All right, because it's now time for News from the Universe, August 2018. Our only story for tonight, because there's just a lot of pieces to it, is this opposition opportunity. Now, what does opposition mean in astronomy? Well, it actually refers to the positions of the Earth and other planets. In this case, specifically outer planets, planets outside. So if this is where Earth is relative to the sun, when a planet is on the other side of the sun in a direct line, that's called conjunction, okay, because the planet and the sun are on the same point in the sky, area in the sky. When it's east directly perpendicular to the sun, that's called quadrature. But the most exciting point is when it is directly online with the sun, and that's called opposition. Why is that exciting? Because that's when it is closest to Earth in its orbit. Okay? And that's when it's closest when we're going to get our best views of it. Now, if I were actually teaching a class about this, I'd actually have these things moving around so you can see the Earth doesn't stand still, right? Okay, the Earth is actually orbiting and such. So it doesn't happen really once per orbit. It takes sometimes a little bit more than an orbit for this to happen, right? But the opportunity this year in 2018 is that Saturn hit opposition on June 27th, 2018, and Mars hit opposition on July 27th, 2018. So both Saturn and Mars are really good viewing this summer. Okay? So, of course, who's going to look at it? Hubble. Hubble's going to take a good look. All right? And so Saturn hit opposition in June. I think we took this picture in late May, and we got a great picture of Saturn here. And this, folks, you want to applaud? Please go ahead. This is one of the best pictures Hubble has ever gotten of Saturn. The detectors are better, but it's also one of the cool things about it. It's the first time I remember seeing a very particular feature on Saturn that Hubble has never observed before in my recollection. Right in here in the North Pole, you see this strange storm system? It actually forms a hexagon. Okay? Let me take that graphic off. Can you see the hexagon there? This hexagon was observed by Voyager, okay, like 40 years ago, and it's still there. This is a stable system on the North Pole of Saturn. And you want to know what? We don't truly know how it forms, okay? We understand that there's some resonances in the winds and everything, but to get a hexagon, we can do sort of things in the lab to explain it, but we don't quite have everything we need to know to fully understand this. So this is a really cool pattern, and this is the first time I remember seeing it in any Hubble image. So here is a movie zooming into Saturn. We took several shots of Saturn, and you can see the clouds orbiting around the North Pole there in that ring. And so I think there's like 6 or 8 images here. And you can see that cloud just at the edge of the North Pole. It repeats. This is not one loop, so it's a repeat of 8 loops. So we got some details of Saturn's North Pole. So Mars also reached opposition. I'm sorry, I forgot this. One of the reasons why we can see more detail in this image than we can see in other ones is that these were done with narrowband images, okay? So the narrowband filters here are listed up here. The blue is F395N, the green is 502N, and the red is 631N. That N at the end of it stands for narrowband, okay? So it's a narrow band of wavelengths. So it's looking at very specific emission from Saturn, which allows us to see more detail. If we just took broadband, wideband filters of red, green, and blue, we really wouldn't see this kind of detail. I mean, Saturn's actually kind of boring when you look at it with just RGB features. But the OPAL program, the Outer Legacy program, that's running on Hubble, and this is one of the first observations of this OPAL program. So I'm told that the microphone is not doing wonders, and I need to switch to the lavalier. Hold on. Okay. All right. So we're talking about the OPAL program, and using these narrowband filters, you're able to see more detail on Saturn. And what Hubble provides that other missions don't is this 20-year, 30-year lifespan in terms of taking a look at Saturn and seeing things over time. So this OPAL program, is this better or is this not? Is that getting in the way? Okay. Maybe that was the problem. We had multiple. Yes, he does. That, folks, by the way, was Grant Justice, okay, who obviously was monitoring the sound and saying, hey, something's wrong with the sound, and having multiple things. No, it was just a random microphone stealer. Yes. All right, I totally lost track of what I was saying. All right, anyway, so we got these pictures. We can see all sorts of cool detail. Plus, as you can see in this, we have 6 of Saturn's moons captured in this image. And if you go to our website, there's actually a small animation that takes those 6 or 8 images and follows the moons as they orbit around, too. All right, so that's something you can find on our website. Let's go to Mars, okay? Now, Mars has a somewhat elliptical orbit, okay? Saturn's orbit is relatively circular. Mars is somewhat elliptical, so that the distance between Earth and Mars changes at different oppositions. And you can see it in this illustration from 1995 through to 2005. This shows the apparent size of Mars, the relative apparent size of Mars at these oppositions, which you can see occur roughly every 2 years, okay? And this year's opposition, 2018, is the largest appearance of Mars since this really big one in 2003. The one in 2003, they tell me, was the largest in like 60,000 years, okay? So that was a really big one. This one isn't quite as big, but it's the largest one. So we're really looking forward to it. Unfortunately, Mars didn't really cooperate. It looks kind of fuzzy, right? Well, that's what happens on Mars sometimes. You get global dust storms on Mars. And about a month before opposition, there was a serious global dust storm. And actually, pictures from about a month before opposition were much fuzzier than this. They actually cleared up a little bit by the time Hubble took their images. So in order to understand features on Mars, we have to give you the annotation. Notice we also got Phobos and Deimos, Mars' 2 little moons, in there. But here's the Hellas Basin, in which you can see the dust storm is totally filling the Hellas Basin. That's a giant impact crater, one of the largest impact craters in the solar system. And you got Arabia Terra. This, by the way, is they marked where the Opportunity lander is. And of course, you have the North Polar Cap and the Southern Polar Cap here. So, unfortunately, Mars didn't cooperate. You can sort of see the same features in the 2016 opposition image. All right, you can see this region here in the middle on 2016, and over on the left over here, but you can't quite make it out. So we created a little video to show you. So here's the 2016 opposition. All right, and now we're going to crossfade to a computer model from the Viking images. All right, we're going to rotate that Viking model image just to show you. All right, and there's the orientation for the 2018 opposition. And there's the image we got from it. All right, so that helps you understand that, yeah, the features are there. They're just sort of buried, okay? However, it could be worse, okay? Just to show you, just in a comparison, it's the same size. On the right, I've added in the 2001 global dust storm. Actually, during opposition, Mars was relatively clear during 2001. But 3 months later, in 2001, we got a picture of a real global dust storm, which shows you just how fuzzy Mars can get. So we didn't get the clearest view of Mars, but we didn't get the fuzziest view of Mars, all right? And if you go to our website, we also have another video of Mars where you see Phobos and Deimos do a little bit of their dance around Mars, okay? And that is our opposition opportunity and our news for August 2018. Any questions that I can answer? Yes?
I noticed that the poles aren't covered. How come the dust didn't cover the north and southern poles?
I'm not an expert on atmospheric circulation of Mars, but I believe that if you look at the center image here versus the right image, you can see that it is somewhat fuzzy over the poles, but you've got a lot of reflectivity in the ices, which makes them shine through. Okay, Mars's atmosphere is 1/100th the thickness of Earth's atmosphere. So it's not like a Venusian atmosphere where, you know, when it gets dusty, you can't see through it, or the haze layer on Titan. Even though it's fully hazy, you can still see through it. It's still a bit transparent. So basically, it adds a tinge to the color on the poles, but it doesn't completely block out the poles. Good question. All right, one more.
They had said that Opportunity had shut down because of the dust blocking the solar panels. Has it woken up again?
The return of the microphone. I'm going to put that just to the side just so it doesn't get... All right, so you are correct. Yes, the rovers on Mars, when a global dust storm, they use solar energy, right? And when a global dust storm hits, they have to shut down, okay? And then, in order to restart them, they actually have to shake the dust off of it. So if you can think of those little rovers sort of shaking like a dog getting water off of it, right? They actually had to program the wheels to go forward and back to try and shake it to get the dust off so they could recharge the batteries. Obviously, they've been successful because there have been several of those global dust storms while we've had rovers on Mars, and they all seem to have come back and worked. So yeah, that's a good point. All right? Okay, let's move to our featured speaker tonight. I'm excited to hear from our speaker tonight. Oh, hold on, I have to figure out this. There we go. Our speaker tonight is Greg Sloan. He has been here at the Space Telescope Science Institute for 2 years. Well, he's sort of half here. He also has an adjunct position at UNC Chapel Hill, right? So half of his time is spent down there. He teaches down at UNC Chapel Hill. He comes to us from Cornell University, where he worked for 15 years on the infrared instruments for the Spitzer Space Telescope. So I have a very hard time imagining anyone more qualified to come here and work on the mid-infrared instrument, the mirroring instrument of James Webb Space Telescope, than someone who's been working on Spitzer for 15 years. It is one of these great things within NASA that we can take the infrared knowledge learned in the Spitzer mission and bring it and apply it to the James Webb mission. And I'm sure that the folks here are just absolutely ecstatic to have you on board. Ladies and gentlemen, Mr. Greg Sloan. We got to get your...
I think I'm on. I think it wants my password. All right, well, those were very flattering comments. I have to point out that there's a lot of people from the Spitzer mission here now working on the mid-infrared instrument. So it's kind of nice to be back amongst fellow combat veterans from a previous mission. I'm just one of many. I haven't been teaching too much at UNC Chapel Hill. I just go down there to get a rest from the intense work here. Which follows me down, I might add. So I'm pretty much working full on doing JWST stuff down there when I'm there. All right, so tonight I'm going to talk a little bit about the fate of stars like the sun. I have this poetic prelude here. So I think that people that do this kind of research have a little bit of an inferiority complex because astronomy to a lot of people consists of three things: exoplanets, high redshift universe, and supernovae. And this is none of those things. So I'm really flattered to see such a great turnout tonight, that people decided to brave leaving their air conditioning behind to come here. And it's cloudy to boot. So anyway, let's get on with it. Also, if you look at your handouts, you'll see that in order to add nice pictures to otherwise boring words on my slides, I've tried to steal as many Hubble images as I can so you can follow along and you can see if I got the captions right on the back. All right, so the talk starts The periodic table of elements. So you can see this is a really nice table I pulled off of the internet. I forgot to put the source down here, which is very bad of me. But what I want to say, this is really nice, it's very complex. To an astronomer, there's a simpler version of this periodic table that looks like this. Okay? So we have, in one corner, we have hydrogen, and then in the other corner, we have helium, and everything else to an astronomer is just a metal. But there's a bit more to it than that, because when the universe formed, except for a little bit of lithium to just confuse the story, the universe was just hydrogen and helium, and everything else, all these metals, come from stars. So I think we've all heard the great Carl Sagan quote that we're all just made of star stuff. Well, this is not poetic, it's absolutely true. And so what I have here is a graph of abundances. This is a log plot, so every, from 6 to 8 is a factor of 100. Those are the abundances in the order of the atomic number of the elements. You can see there's a nice zigzag pattern here where all the even numbers have a bit more abundance compared to the odd ones. I'll explain that in just a sec. And then over here, for people that really can't stand figures like this, I just sort of laid it out as a table. So you can see that very quickly, hydrogen is 90% of the universe. This is by number. I think that Frank had put a slide up a couple of months ago that was by mass. So the numbers are a little bit different, but so about 91% hydrogen. Most everything else that's left is helium. Oxygen weighs in at a hefty 0.5%. And then it's just downhill from there. Carbon is next, and then, at 0.1%, nitrogen is just ahead of neon. And then from there, it just plummets quickly. And then you can see this. So basically, in green right here, that's what the primordial abundances of the universe look like right after the Big Bang. And this is the plot now. So all this blue stuff here, everything above the green, that's all made by stars. So astronomers, since everything in the universe except hydrogen and helium is a metal, we like to talk about metallicity, which is just the abundance of everything that isn't hydrogen and helium, or the abundance of everything that's made by stars. So I'll be using that word a lot, metallicity. That piece of jargon I cannot drop. I apologize. Okay, so our first pop quiz question for the day, and because we don't have car talk anymore, I adopted their enumeration. So, what is a star? So how many people, we'll go through this. And so 1, if you agree with 1, raise your hand. Something that shines, which means it emits more energy than it absorbs. Let's see some hands here. How many people go for 1? Okay, definition of a star. That's a few people. That's like what? A quarter of us? Let's go for B, something undergoing nuclear fusion reactions in its core. There we go. So that seems to be, I think that's already the winner. And then Roman numeral 3, an ultimately doomed battle with gravity. But I see that I'm not on the winning side. So 1 is not so good because actually Jupiter emits in the radio quite a bit of energy. And I actually had an answer for the question that you were going to come back to on the rogue planet. That's 20 light years away. It's in the news because they picked it up. It was discovered in 2016, I think, and I forget by whom. I don't know that story. But they picked it up with the VLA, the Very Large Array Radio. They picked up the aurorae that it must be giving off. It's got a really strong magnetic field. Yeah, so Jupiter does the same. Jupiter emits a lot in the radio and emits in the far infrared. So Jupiter would qualify as a planet by number 1, but it isn't. A star by number 1, but it isn't. So B is certainly good. I like 3 because the real point is that the moment that a star starts to form, which means the moment that an interstellar cloud is compressed just enough to be self-gravitating, from that point on, that poor object is doomed. It is eventually going to wind up as a degenerate object, either a white dwarf, imagine half the mass of the sun packed into an object the size of the Earth. That's a white dwarf. Or a neutron star. Imagine an object the mass of the sun packed into something the size of Baltimore. Or a black hole. Imagine something even smaller. Right? So that's what's going to happen. So basically all these things, all these stars that we see, they're just at some stage of that battle. And they're going to lose. So here's their fates. I apologize in advance. I realized when I was going through this today, this is my busiest slide. Anyway, so we have this broken up into 3 mass categories. If it's 25 solar masses or up, so 25 times the mass of the sun or up, and that's a really rough number because we don't really know. It might be 30, it might be 40. If it's really honking big, to use the technical term, it will become a black hole. But I shouldn't say it. The core of that star will become a black hole. 90% of the star will be dispersed back out into space, back into the interstellar medium. But the core of the star will become a black hole. I think the core has to be about 3 solar masses or so, and then that's enough mass to overcome any force that we can think of that would hold this object up. If it's between some number, we don't really know, 8 to 10 solar masses is kind of the bottom end of the range, and up to 25, or I said 30. If it's in that range, it will go supernova, get all the headlines, get all the attention, make me very envious, and it will become a neutron star. So I'm focused on the objects that are less than 8 to 10 solar masses. Those are oh yeah, here's a picture of a supernova. This is supernova 1987A. There's a picture of some fun things happening around a black hole. Please don't ask me what they were because I just thought that was a pretty picture. That's about all I know. Sorry. But if it's 8 to 10 solar masses or less than that, it will become a planetary nebula. Lots of good planetary nebula pictures on the handout. And the core of that star will become a white dwarf. In the case of the sun, the white dwarf will have about half of the mass of the sun, and the other half of the sun's mass will be ejected back into space. And at the upper end of this range, 90% of the mass of the star will get ejected back into space. But it's not just we'll get to that. So let me just keep going. So how do stars hold themselves up while they're doing it? Well, they do it by nuclear reactions, by fusion reactions. And I know you guys didn't really come here for a lesson in nuclear physics, so it's just the one slide. But I just want to sort of review this just really quickly. The basic reaction is hydrogen fusion. Now, there's a lot more to it than just this. You basically take 4 protons, 4 hydrogen nuclei, and through a few backflips and contortions and a few other reactions, you wind up with a helium nucleus, this guy, right? It's ionized, so there's no electrons, just this alpha particle. 2 positrons, some neutrinos, I don't remember how many, I think 2, but yeah, because of the positrons. And then a whole bunch of energy, which is the point to the reaction. And so the sun is fusing hydrogen to helium in its core, and it can keep doing that until it starts to run out of hydrogen. And then things get interesting. The next reaction that's going to happen is called the triple alpha reaction. 3 helium nuclei, 3 alpha particles, hence the name. And that will produce, you put 3 of these guys together, you get carbon, and again, a lot of energy. And these stars are going to keep trying to find new sources of energy in their core to hold themselves up. Otherwise, they keep collapsing. And so the next one up is alpha capture. So if you take a carbon atom and you add 2 more protons and 2 more neutrons, you get oxygen. Do it again, you get neon, etc. And you can also do proton capture, which is how you get to the odd numbers. Now you can start to see why that corrugation and the abundance exists. There's more of the even numbers because alpha capture happens a lot more than the proton capture. But those only happen in the really massive stars. For the sun, the last hurrah is the triple alpha sequence. And this is a really cool diagram. This is a really cool periodic table done by Jennifer Johnson at Ohio State. And this is sort of our best attempt to explain where all of these elements come from. So yellow is the one I'm interested in because those are dying low mass. This should be dying low and intermediate mass stars because basically everything that doesn't go supernova. And you can see that carbon and nitrogen, which are the 2 of the top 5, are primarily made by these kinds of stars. So without these kinds of stars, there's not going to be a lot of carbon and nitrogen out there. And you'll remember, carbon is the element of life. So none of those, you got to wait a bit after the universe forms. A supernova ain't going to do it for you. You got to wait for these lower mass stars to evolve and start seeding the interstellar medium. Okay, switch gears here. I like this plot, partly because I made it. But So basically, I've got some black bodies. A black body is just a theoretical object of a certain temperature, so it's like a perfect spectrum. You can see in a minute. Well, I'll just show you now. Those are stars. Those are black bodies. So, it's close. For physicists, this works pretty well. So what I want to point out here, so we have wavelength on this axis. I'm going to do this a lot because I'm actually a spectroscopist. So I love spectra. And I have to tell you that whenever we're dealing with the PR people for a telescope, we drove the Spitzer PR people crazy because we had all these we thought, really newsworthy events, with our findings and whatnot. And we say, well, just plot the spectra, the squiggly line. And they're like, people don't want to look at squiggly lines. So I apologize because I have a lot of squiggly lines. So what I have on the top is different temperature black bodies. And the point is that a 38,000 Kelvin black body peaks at a wavelength of like 0.1 to 0.2 microns. That's about 1,000 to 2,000 angstroms. That's the ultraviolet. That's toasty ultraviolet, okay? And then you take a red giant star, which is about 3750 K, something like that, and that peaks over here at between 1 and 2 microns. That's the near infrared. Here in the middle, by the way, these are sort of an average response function for the 3 different types of detectors in your eye, the red, green, and blue. When I first made this plot, it finally dawned on me, I never understood how people could be colorblind. But now I get it, because you can see that the red and the green responsivities in your eye almost overlap. And some people, they do overlap, and those people can't distinguish red and green. So probably not the best design from the get-go, but eyes work pretty well, so I'm not complaining. Astronomers have decided that this is not the ideal filter set. So here's one example. These are the Johnson filters. How many people here would call themselves amateur astronomers? Just a handful. Do you guys work with Johnson filters at all? Not too much? Okay, well, it's probably better. But so very standard set. So you sort of separate things out. UV, ultraviolet, blue, and visual. And then they call this infrared, but this is like near optical. Infrared's over here. And then some near-infrared filters, which are known by their letters JHK. You notice they're sort of out of order because people kind of added these things. And anyway, so these are real stars. And you can see that you want to use infrared filters. If you want to look at red giants, you want to be out in the infrared, near-infrared, because that's where all the energy is. So you can much easier to detect them out there. And this is just another filter set. This is the Sloan filter set, not named after me, named after Alfred P. Sloan? Alfred P. Sloan Foundation. Yes. Named after that foundation because they funded the Sloan Digital Sky Survey, which I have never figured out how to capitalize on. But this is a different filter set. And in a second, I'm going to show you some the results of some data taken with the green, the G, and the I filters. But you can see lots of filter sets out there, and people love to argue over which one's best. These are the things that keep astronomers entertained. All right, so here's a picture taken from a 32-inch reflector at Mount Lemmon in Arizona. This is the globular cluster M5. This is a paper which has been hanging fire for me for a bit. But we're working on it. It's not my data, but we have a different image. This one's much prettier. And the one thing I want to point out is when you look at it, you can see there's some objects. Some of these stars are very red, and then some of them not so red. And these red ones are also very bright. Those are the red giants. Those are what we're interested in. And so basically, the globular cluster just is about 1 million stars all packed together in a nice tight ball. Okay, and the key points are they're all about the same distance from the Earth. So when I start plotting these things up, I don't have to worry about everything getting smeared out because some are closer or further away. They're all about the same age. In this particular case, 10.6 billion years, roughly. Thanks to the Hubble Space Telescope, we've actually learned that they're not all exactly the same age because there's actually multiple epochs of star formation early in the game. But by 10.6 billion years, this guy was done making stars. And also the same metallicity, which is very low, less than 1/10 the solar metallicity. So these guys are full of metal-poor stars and very old stars. And so this is a great picture, but actually for an astronomer, what you want to do is you want to actually start plotting how bright they are versus their color. And that's called the color magnitude diagram. A lot of you guys are veterans of these talks, so you've probably all seen this before. I just wanted to make sure we had our bases covered. But basically what you do here is you take the magnitude in the G filter and you subtract it from the I filter, and that's a color. And the redder the object, the further it's going to be over to the right, the bigger, the more positive the color that you get. And the bluer, the smaller, or even negative the color. So blue stuff is on the left side, red stuff is on the right side, and then how bright it is, bright stuff's on the top. So I wanted to pick this diagram apart, because all these stars are the same age. If this was a young cluster, you would see a diagonal stripe that would start here with this bunch of stars on the bottom. It would go up and to the left like this, and that would be called the main sequence. The most massive stars burn out first, and they're at the top of the main sequence. This is a very old cluster, so most of the main sequence is gone. Stars are dead. All you have left are the low-mass stars. So if we sort of start, we have our main sequence pointing to it, right down here at the bottom. The main sequence turn off is this point where the whole sequence starts to bend a little bit to the right. Those are the stars that are just now running out of hydrogen fuel in their core. So they can no longer hold themselves up. So they just spent, in the case of the sun, 10 billion years, happy as clams, burning hydrogen and helium in their core, nice and stable. You know, the star's nice and stable. The planets, you know, who knows how many wars and stuff been happening, but the star is pretty stable. So when it runs out of hydrogen in the core, the star will ascend what's called the red giant branch. And that'll take about 1 billion years for the sun. And this is actually, things start to get weird really quick. So you have to think of a star as two parts. There's a core, and then there's an envelope. All right? And they evolve separately. The core is, all the actions in the core, the envelope just responds. So what happens is, if the core can't hold itself up anymore, what's it going to do? It's going to contract. Collapse is a little fast, because it takes 1 billion years, but yes, it's going to start collapsing, because there's nothing to hold it up anymore. Gravity is just smushing it. So as it collapses, as it contracts, it's going to heat up. And as it heats up, even though it doesn't have any hydrogen in the core, it's still burning hydrogen in the shell around that helium core. And the luminosity actually goes up. The star gets brighter. And because the luminosity goes up, the envelope responds because you got all this radiation pressure trying to get out. It pushes the envelope out. So the core contracts and the envelope expands at the same time. And you get a red giant, a big, fat, fluffy star. And after 1 billion years, the star gets to the tip of the red giant branch, and now it's hot enough in the core to ignite the helium reaction. And when that happens, the star reconfigures really quickly. It's called the helium flash, and winds up over here on the horizontal branch, which you could also call the helium-burning main sequence. And so it's nice, it's a stable place again, but it's only got about 100 million years before it runs out of helium in the core. And then it does exactly the same thing. It goes back up the red giant branch a second time, this time with a really complicated structure, because it now has this inert core of carbon and oxygen, surrounded by a very thin shell of helium, which is being fed by a hydrogen-burning shell outside of that. And when you get enough helium, the helium will actually ignite, and you'll get more of that triple alpha sequence. So it's like an onion. And for most stars, this is because they don't have enough mass, the temperatures don't get any higher in the core. This is it. There are no more nuclear fusion sources for them to work with. So when they collapse the next time, they're toast. And maybe 1 million years for the sun to basically climb back up this second giant branch. This is one of the most, so this is called the asymptotic giant branch because it asymptotically approaches the first giant branch. This is the worst possible name I can imagine in astronomy. So what do you study? I study asymptotic giant branch stars. And it's like, okay, well, I'm going to go get some more coffee. The only thing you do is call them AGB stars, but I've always been taught you can't just start using acronyms without defining them. So anyway, this needs a PR rethink, in my opinion. I want to call it the death branch. We'll see how that goes. So this is just a nice picture sort of illustrating what the sun would look like at different stages of its life. You notice that, oh, I have a cursor. Let's get that cursor, make use of it. It went away. It won't come back. Okay. There is, you can, there are 4 pixels lit up right here. That's the sun. These images are actually 200 pixels across, which is the size of the Earth's orbit. And so you can see that RGB, big, horizontal branch, small again, but not as small as the main sequence. And then early AGB, really big. This works out, that's about 0.9 AU, or 9/10 the radius of the Earth's orbit. And this is early AGB. Things get worse. All right, but before we get to that, let's look inside this guy. Remember I described to you this crazy multi-shell geometry. Well, this is what it looks like. So on the left, we've actually got this plotted not with radius, but with mass to sort of tell you how far you are along going from in to out. So you can kind of see all the different parts. You're halfway out, that's because half the mass of the star is in the core. But if you really want to see what it looks like, look on the right-hand side. It's all right down here, really kind of small. So these are really interesting creatures, these AGB stars. They're these giant, puffy, tenuous, almost vacuum stars that will expand, in the case of the sun, to engulf the Earth. Asymptotic giant branch. How about death branch? I'm kind of liking this. We might go with this. So this core will become a white dwarf, and the envelope will get ejected. So I said that the helium doesn't burn continuously. So the helium will build up, and then there'll be this, what they call a thermal pulse, this runaway nuclear reaction where this triple alpha sequence takes off. So what I did, Peter Wood and his student, somebody, I don't remember Vasiliadis. I've never met Vasiliadis, so I don't know his first name. But this is a 25-year-old theory paper, and it's still pretty darn good. And so what he's done here is he's basically plotted the temperature of the star on the top, the log of the temperature, the luminosity, the pulsation period of the star. I'll get to that in a second. That's not the thermal pulse. The expansion velocity of the star, its mass. This is kind of fun because you'll notice after a few of these thermal pulses, the star hangs in there, and boom, it loses half its mass pretty quickly. We don't actually know how that happens. The way Peter made this work, if I remember right, and since 50,000 people can see this, or something like that, 5,000 you said. That's enough. One of them might be Peter, and he's going to be mad at me because I think he just turns on the mass loss dial to make the mass loss happen. It's a little bit better than that, but basically we don't really understand that process, and that's pretty important. So anyway, the point is, every time this thing goes through a thermal pulse, it reconfigures itself for a little while. And what happens is, the envelope of these stars is completely convective. That 99% of the star that's just envelope, it's convective. You've got convection cells going all the way from the center out to the Earth's orbit, basically. And what happens in the core, when you get one of these helium flashes, there's a little convective layer that forms there. And it overlaps with the convective envelope. So these stars, they're making carbon via this triple alpha sequence and dredging it right to the surface of the star so it can be ejected into the interstellar medium. And that's where the carbon comes from. According to Ms. Johnson's plot, about 75 or 80% of it. So we have thermal pulses on the inside happening for the sun like every 80,000 years, something like that. We know this happens theoretically. We're on really solid ground. It's not clear to me that we have clearly said, oh, that star just had a thermal pulse. Because it's actually really hard to see because it takes, thousands of years for these stars to kind of reconfigure themselves. But we do see the envelope is, as I said, this big tenuous thing stretching all the way out to the Earth's orbit. It's really unstable to just simple pulsations. If you push out, it keeps going, and then it will fall back in. So the whole star, basically, is pulsating like this on a time scale, in this particular case of Chi Sig, with a period of 405 days. So over the course of a year and 40 days, it will pulse out and pulse back in. So Chi Sig, if you catch it at maximum, is a naked eye star. It is magnitude 3 or 4 at maximum. But when it's at minimum, it's like a 14th, 13th magnitude star. There's no way you can see that with your eye. So these are huge, major pulsations. Where did I put it? Yes. So as I said, these stars are going crazy. inside and outside. So we were interested in digging into this a little bit. So we took M5 and we did our photometry, but we didn't do it just once. We kept getting more time over the next couple of years to sort of track which stars were the variables, which stars were pulsating. And you can see that we got a whole bunch of guys on the horizontal branch. Those are our Lyra stars. Those are like a standard candle. They're really, that's how we figured out that the sun wasn't the center of the Milky Way. I didn't do it. This was like, 80, 90 years ago now, I think? Something like that. But you can see out here, as you climb up the red giant branch, you can see that the variability really does increase all the way to the tip, and that's pretty cool. So we were all really proud of our multi-epoch photometry, but if you really want to see multi-epoch photometry, the Gaia mission is stunningly impressive. I mean, this is this is art as far as I'm concerned. So this is their color magnitude diagram. They've got blue and red filters. They call them BP and RP. They didn't ask me. And then absolute magnitude here. So the nice thing about Gaia is because it gets parallaxes, so they can correct for distance and put all the stars in the solar neighborhood, all gazillion of them, on the same plot. So here's the main sequence is like right down here. Here's the giant branch, and this is basically color-coded by variability. So way up here, here's the RGB and the AGB, and you can see that they're all variables. This plot over here on the right-hand side is kind of fun because what they've done here is they've mapped known identified variables back onto their diagram. So long-period variables is what all these guys are. These are all AGB stars pulsing like mad with periods of anywhere between 100 days and 1,000. And those are stars in the midst of ripping themselves apart and blowing their innards back into space. Okay, so switch gears again. When a star gets cool enough, molecules can form in its atmosphere. So here we have a nice picture. This is the Hyades. That's the V of the face of the bull on its side. That star right there is Aldebaran, Alpha Tau. When I started doing astronomy, infrared astronomy at Wyoming, where I did my PhD, I never really appreciated that the stars I was going to be looking at were naked eye objects. Because Alpha Tau was what all of our calibration hung off of. So this is the star in the infrared. So basically the spectrum is dropping off. You see there's a couple of kinks in the spectrum here. And this is not the best way to plot it because what dominates the fact is the fact that it's very bright at 2.5 microns and very faint at 20. So what I've done is I've got another plot come up here where I basically multiplied that spectrum by the wavelength squared to kind of flatten it out, to bring out some of the detail. So here you go. Now those kinks are these really deep molecular absorption bands from carbon monoxide and silicon monoxide, 2 of each, overtone and fundamental, here at basically 4 microns and then at 8 microns. And then here's another star, an even cooler giant, and I've spread it out. So this just goes from 2.5 to 12 microns. But now you can really see the carbon monoxide, the SiO band, CO, water vapor in these coolest stars. And this is important because what's going to happen is when these stars start pulsating, remember they're expanding, and they're getting smaller. And when they're expanding, there's a bit of a kick of velocity outward. And if these molecules can get far enough away from the star, they'll actually cool enough so that dust can condense out. And the opacity, how opaque dust is compared to the same bunch of molecules as a gas, it's sort of like they all just drop their sails, and the wind's kicked up and they just get blasted out. So when you start making dust from these molecules, then the radiation pressure from the star just blows it out into space. And that's how these stars shed mass. So here's a really complicated diagram to explain everything really simply. I'm going to see Josef Hron in Vienna in a couple of weeks, and I'm not going to tell him that I put it that way, because it's actually a pretty nice diagram. So basically, if you just draw a line through the middle of it, cutting it in half vertically, the upper half is oxygen-rich, and the bottom half is carbon-rich. And what it's doing, and if you go from the left side, that's the center of the star, but it's all like in log space, so you can cram a lot of dynamic range into one plot. convective envelope, you go a little further out. Now you're out in the pulsating atmosphere. That's where the molecules are. And you get further out, that's where the dust is. The whole point to this plot is basically to show you what happens because the first molecule that forms is carbon monoxide, CO. And the CO will keep forming until it runs out of one of them, carbon or oxygen. So remember these stars they've got these thermal pulses in the core. They're dredging up carbon to the surface. They started out oxygen rich, but every time that they do one of these dredge ups, there's like an extra delta in carbon. And if they do it enough, they'll have more carbon than oxygen. So the CO forms, and it uses up all the carbon, and you're just left with oxygen as the free molecule to make all these molecules and to make the dust. So you get a lot of silicate dust and alumina dust, just like on the beach, just a bunch of silicates. But if it's a carbon star, all the oxygen is consumed by the CO, and you're just left with carbon and other elements. You can make acetylene. There's a lot of acetylene in these stars. No smoking. But it's okay, right? You can't burn anything because the oxygen's all gone. And the acetylene can make amorphous carbon dust. So my focus as an infrared spectroscopist has always been the dust. And these are what the spectra of these two different kinds of evolved stars look like. So on the top, these are infrared spectra, like the visible part of wavelength space is over here. It's not even plotted. So here's the star, and now you have these emission features from all of this hot dust around the star at 10 microns and 18 microns. So you get those two emission features in your spectrum. Ooh, I'm looking at silicate dust. That was easy. And then, if it's a carbon star, you can see silicon carbide dust at 11.5 microns. But what's actually most of the dust, so in this spectrum of the oxygen-rich star, that's actually the star. That's the photosphere of the star, plus some dust. These carbon stars, the dust is so opaque, you can't see through it. What'd I do? Oh, man. And what I really want is remind me never. That's crazy. I actually, my usual computer is a Linux system, and I feel like I have kind of control over it, but my MacBook thinks for itself, and I don't like that at all. So anyway, the amorphous, so all of the what looks like the star here, all of this stuff, between the emission and absorption features, that's actually the amorphous carbon dust. Amorphous carbon has no features at all, except that it's just dark. It just blocks everything underneath it. So I'm going to skip this. This is all about the oxygen-rich dust, and it takes us back a couple of decades when I was studying it. But lately I've been doing the carbon-rich dust. I feel like I'm going on, so I'm going to cut one slide out to shorten the talk ever so slightly. So I want to focus on the ashes to ashes part. So this is a planetary nebula. This is a carbon-rich planetary nebula. This is NGC 7027. So that was a carbon star once. And the point is that the sun doesn't have enough mass to become a carbon star. It has to be about twice the solar mass, up to 5 times. In that range, those guys will all become carbon stars one day. And as I've already explained, they're the source of the carbon in the universe. And if we could understand better how these stars die, we would have a better handle on when, in the history of a galaxy, you'd actually have enough carbon for life to form. We actually don't understand enough to tell about how these things die. Because basically, what I think happens is that as soon as you dredge up enough carbon and you cross some limit, the star basically just goes into blowout mode. And I'm not the only one that thinks this. This is not my idea originally, but I'm certainly on board with it. But it's really difficult to demonstrate that that is true. We haven't done that yet. All right. The way we've been tackling this problem is we've been looking at the local groups. This is a really nice illustration. You can see this, we have Andromeda, M31, up here above the plane of the local group. We've got the Milky Way right in the center. Since we drew the plot, we're allowed to do that. But around each of these two big spiral galaxies, there's a whole swarm of dwarf galaxies. And most of those dwarf galaxies are very metal poor. They haven't formed a lot of stars in a long time. And so they're sort of like, they're kind of a proxy for what galaxies would have looked like at very high redshift early in the universe. Metal poor galaxies. The only problem is that most of these dwarf galaxies, they stopped forming stars a long time ago. The holy grail would be to have a metal poor galaxy that just formed some high mass stars. because those are the ones that we would be more interested in. But we'll take what you can get. So we've been looking primarily in the Magellanic Clouds, the large and small Magellanic Clouds. The Large Magellanic Cloud has a metallicity about half solar, which is sort of like the outer parts of the galaxy, but still a lot less than most of the stars in the galaxy. And the Small Magellanic Cloud is about 1/5 solar. Let's focus on the Large Magellanic Cloud here, because that's the one I got slides on. So again, I've got a really nice snazzy picture. I pulled this off the web. Thank you, John Gleason. I should have asked for permission. I hope he's okay. Good advertising, right? And then I have a color magnitude diagram like what I put up before, except this time it's a near-infrared color magnitude diagram. And there's so many stars to plot that they chose to make it a contour plot. So here's the peak, right, and there's the next contour all the way down. I really like this plot because it's sort of like this giant hand with this thumb sticking out. And this thumb over here, that's the AGB. That's where all the dying stars are. Dave Riebel, who got his PhD here at Johns Hopkins a few years ago, took a closer look at the LMC, and he took all of the AGB stars and he plotted them up on this diagram. So here's the old diagram and here's his diagram. So basically, red is carbon star. So you can see that thumb, that's the carbon stars. So these stars are incredibly red. I mean, they're so red that actually, like they're absorbing infrared light. And so these stars look like they're getting fainter out here at the reddest ones, but they're not. They're just, the light can't get out at 2 microns. It has to get out at longer wavelengths. So, of course, I do spectroscopy, so here's some spectra of what these guys look like, plotted from top to bottom. This is the bluest carbon star, and then every color is sort of like a degree of redder, all the way down to the point that the dust is so thick that even the silicon carbide feature has gone into absorption. It's not emitting anymore, it's absorbing. That's a lot of dust. And and then also you can see there's an absorption band from acetylene molecules. That's the stuff that makes the dust. And we spent a lot of work on these kinds of spectra. But I'm not going to show you too much of that. I'm going to show you some photometry. We're almost to the end. I think it's like 39 or something. So this is not a color magnitude plot. This is a color plot. So what we have here is what color it is between 3.6 and 4.5 microns on this axis. And on this axis, between 5.8 and 8 microns. And then it's kind of colored by the color I got from the spectra I just showed you. And the whole point here is that for most carbon stars, if it gets red in one color, it gets red in another. And it's a pretty tight relationship all the way up here except for at the very end. The reddest stars at the longest wavelength, they're a little bit too blue at shorter wavelengths. Like some light is escaping from this system. And if you look at, this is a plot of how variable they are. That sigma, that's basically you keep taking data at different times, and if the numbers are bounced around all over the place, that's because it's a variable star. So you can see for most of the population, the dustier they get from 0 to about 1.5, the stronger they're pulsating. All makes sense, right? Lots of pulsations, lots of dust. But then all of a sudden, the reddest ones are hardly pulsating at all. The hypothesis that we put out there is that's because they've stripped their envelope. There's nothing left to pulsate. So basically, it's just a white dwarf core, almost, inside this really thick dust shell, except the dust shell is moving outwards, and the asymmetries are starting to show, so blue light is starting to escape through scattered emission. We think we're looking at systems like this in the Large Magellanic Cloud. This is in the galaxy. This is AFGL 2688, or the Cygnus egg. So there's a really thick dust line here, but there's all this light that's getting out the poles of the system and then scattering into our line of sight. So basically, my point is that these guys up here that have moved off the carbon sequence, we think we're catching them in the very act of dying. The problem is that this is a spectroscopic sample. Like, we chose to look at these guys because they were interesting. So this is a biased sample. So I can't make any statistical conclusions from this sample. So we have to go back and look at the larger photometric sample. As a spectroscopist, I hate that, but that's the way it is. All right, so this is basically how the stars die. And then I just wanted to add this amorphous carbon that they're spewing into space is made up of little pieces of other types of hydrocarbons. And you can see that when the star actually, when the white dwarf at the center is exposed enough, you can see it cooking the dust from the inside out. And then you can see this is the discovery spectrum taken 20, 35, 45 years ago now, Fred Gillette and company. The infrared spectrum, they have all these bizarre emission features from this planetary nebula and then NG 7027, which I showed you earlier. And this is another spectrum from another source. But basically, we're looking at these things called polycyclic aromatic hydrocarbons, which are very small pieces of carbon. So I put one up here. They don't put the little C's at all the vertices of these hexagons, but these are basically hexagons made of carbon. They're little molecules. They're big molecules or small dust grains, depending on how you think of it. And we see these things everywhere. And when you start looking at molecules like this, my last slide is the next one. Look up here, right? Those are two of the base pairs for DNA. So let's just go back for a second. There's some differences. These are just carbon. So technically, this is organic chemistry by definition, right? But that doesn't mean there's life. Because the key point to the DNA base pairs is that a lot of nitrogen substitutions have happened, and there's also some oxygen. And you'll notice that this is a 5-membered ring, not a 6-membered ring. You get the idea. But the point is, my point is this carbon-rich chemistry that we see in the outflows from these carbon stars is incredibly complex. Now, we haven't detected the spectroscopic signature of the nitrogen substitutions, but that certainly is something to keep looking for. Anyway, that is all I had. Thanks for putting up with me for too long. Okay, now what?
You get to ask, call on people with questions, and I get to be microphone delivery guy.
Oh,
Is the microphone? Oh, it is on. Okay, good.
I wonder if anybody can speak like in an alto voice with that thing. All right, I see a question way in the back. See if your work cut out for you.
Thank you. All the way back there. All right, we're gonna have to pass this over. There you go.
But Lord help us.
I think you quoted a figure of 80,000 years for pulsations at one
For the
point.
thermal pulses, the time between two consecutive ignitions of the layer of helium in the core of the star. Yes.
But then the long period variables, their pulsations are a year maybe.
Right.
How does one get to the other?
You don't. They're completely separate. One of them is something going on in the core of the star, and the other is just basically just a dynamic pulsation going on in the atmosphere. It's unfortunate that they decided to call these things thermal pulses. I mean, what else could we call them? Because it's a runaway nuclear fusion event in this thin layer of helium in the center of the star. So it takes about 80,000 years for one solar mass star to build up enough helium to do this. But the point is, whatever they're doing on the inside, these stars are also like breathing on the outside.
Okay, thank you.
Sorry about that. Astronomers are really bad at naming things, you might have noticed. Over here, where was the one over here? Is that you? Oh, hang on. We'll get it. We'll get there. I'm sorry.
Can you
Slide that shows the progression of a dying star,
The progression of what?
the death of the star, the different reactions.
Oh, that was early.
Yes, it was.
Boom. That one. Yes. Okay. Question. You had a question.
Oh yeah, I just wanted to ask: Can new planets accrete around white dwarf stars from that ejecta?
That's a good question. I don't know the answer. My instinct is no, but my batting record on instinct is not so good. I do know that Mike Jura was one of the people that sort of got this field started of looking at the accretion of material from planets that have been ripped apart onto white dwarfs, but that's not the process you're talking about. If you had enough mass, then you could do it, but my question is, where would that material be accreted from? Probably another planet, so it'd be hard to remake one, but yeah, I'm not the expert on this, so my apologies. I have to follow the man with the mic. Yes?
I'm a little confused perhaps about the relationship between the development of these heavy metals and molecules from the individual, complex molecules from smaller molecules, and also what you referred to as dust. Is dust just conglomerations of these heavy metals in various,
Yeah, so if you think of the sun, so the sun was already born with lots of oxygen and silicon, right? So it added some carbon, but it already had a lot of oxygen and silicon to start with. And so as it ages out, yeah, it pushes these elements out. They bind into molecules, and then those molecules will bind together into dust grains, provided it's cool enough.
So all the interstellar dust, all the interstellar dust that's floating around is related to the manufacture as the star is made and through its death spiral.
So you just put your finger on a really difficult question to answer. The question was, so just if we make dust around stars and we have dust in the interstellar medium, is it the same dust? And the answer is apparently not. That apparently there's a lot of controversy about this right now, but the idea is that supernova explosions are really efficient at destroying dust. And so if you actually start adding up how much dust supernovae have to destroy, it's like all of it. So there must be another source of dust formation out there, like maybe the dust is being formed in these clouds. I'm a bit of a skeptic about the fact that supernovae are destroying all the dust, but I do not have a good quantitative, really well-grounded theoretical argument against it. I just don't like it. And that's not good enough. But there's a bit of a debate about this. So it's not, the answer to that is not clear. And that is unfortunate.
Does the dust carry all of the molecules?
All the ones,
Interstellar space.
all of the ones that can form into dust, yes. But like the neon is just a noble gas, right? So the neon just has to get dragged along with the process as a gas, for example. Which does happen. Because these dust grains get accelerated, they start slamming into gas molecules and dragging, or gas atoms and dragging them with them too.
Okay, who's next?
Who is next? Right here, yes. Wait to receive.
What happens to the dust? Can the dust form planets?
Yes. In fact, the dust appears to be a key part of planetary formation. But not necessarily, as I said, we're having a bit of a difficulty understanding the path of the dust in the interstellar medium. But once you have a star starting to form, the cloud that it's in has a lot of dust with it. So the dust will form into a disk, and then the planets will start to basically form, you'll get planetesimals, and you'll get planets forming, and the dust appears to be a key part of that process. There's some debate about, is Jupiter, there's been some debate whether the Jovian planets are actually just gravitational collapses of gas, or whether you have to first have a terrestrial core formed from accumulating a lot of dust particles. I think that was an open question the last time I looked carefully. So the short answer is, yeah, dust. You need dust to make planets.
All right.
Just to make my life easier, I'm going to go to someone nearby.
In one of the last slides, water is being formed.
Yes.
Is that evaporated or?
It's water vapor, so it's gaseous.
Is that what's formed with what do you call it? Those ice giants.
Red giants.
Yeah.
Yeah. So yeah, in a really cool red giant, you can see this water vapor. We actually, a colleague of mine, Kathleen Kramer at Boston College, and then some colleagues at UC Davis, Matt Richter, we have a proposal in, and I found out today that we're going to be looking at very high spectral resolution at some of these water vapor lines in some of these red giants using SOFIA, which is the airborne telescope that flies out of California. And the hope is that we can get enough information to work out how far above the photosphere this water vapor is, because there's a big debate. Is it in clouds? Is it in the? So we're hoping to address that. So, yeah.
So on that last slide, there was an adenine-thymine complex. Feedback, sorry. So is there actually evidence that there is that complex coming from stars? And I'm curious. I'm not familiar with the idea of such complex molecules coming right out of stars. I always thought that they were being formed on Earth, but I'm curious what more evidence there is about stuff like that. That's really interesting.
If I remember correctly, an amino acid has been seen using its radio emission. They've been able to identify this is an amino acid. But some of the amino acids are fairly simple, and you can see some of the molecules we're seeing are pretty complex. So.
Hi, I'm wondering if you have any thoughts on the fact that there was a hexagon on top of Saturn, and then your last two slides had hexagons.
I knew
Yeah, these hexagons keep popping up. So the question, I don't know if you guys catch the question, is there any, just we had a hexagon on Saturn's North Pole. We got carbon arranged in hexagons. I will just say that, before we had PowerPoint presentations and I was doing these with overheads, and I would take my talk in a big stack of overheads, I would have a little envelope I bring along. I would do little cutouts of chicken wire because it's a hexagonal shape, right? And you'd cut the links to be like the hydrogen bonds, and I would pass those out so people could kind of hold coronine and other pause. Yeah. So I think the common thread here is chicken wire.
And symmetry.
Yeah, can you describe in graphic detail, as much as you can, what's going to happen and when our star, our sun, starts to die?
Well, my wife and I have been discussing if we should keep investing in real estate. So the process will let's see, we are 4.6 billion years into a 10 billion year process, right? So in another 4.2 billion years. And the problem is, 10 billion years, there's an error bar there, right? And it's probably plus, I'm going to just wager a guess, it's 500 million years, plus or minus. Then at that point, the sun will start to ascend the red giant branch. But actually, the scary part of all of this is that, you remember the part I said is that as the core collapses, as the core starts to contract, then the luminosity of the star goes up. That's already happening. Yeah. So every day, the sun is just slightly brighter and hotter than it was before, right? So, the climate change caused by the burning of fossil fuels is just making an already slowly deteriorating situation worse, right? We're just adding to the problem. So I guess one of the ways to look at it is that since we clearly can't stop consuming fossil fuels, we're going to have to figure out some other way to mitigate for the problem. I don't like that solution at all. I would just say, how about fewer fossil fuels? That'd be nice. But the point is,
we're going to be fried. We're going to be fried before we burn, so to speak.
Yeah, we'll be fried before we burn. That's good. Yeah. But I guess what I'm getting at is that we're going to have to figure out how to mitigate for the fact that the Earth is warming up in the long term anyway, because the sun is going to get hotter over the next million years. So now we have, now we need to get a little bit of a head start because we can't stop burning fossil fuels. So
in my experience, the estimate is that the Earth is totally uninhabitable by about 3 billion years from now. Is that the number that you had in your? That's why
I don't know, actually.
I mean, no matter what humans do, the Earth is uninhabitable in 3 billion years, but before it starts going up the red giant branch.
Yeah, something like that would be, I think that'd be true. All I know is that Mars does not look particularly appealing right now, but
Okay, you had.
Oh yeah.
you have to get his attention. Yes.
A quick question about variable stars. So when you see a variable star, is it always an AGB?
There are many, many kinds of variable stars. For example, you could have two completely normal non-variable stars that are in a binary system, and if they happen to eclipse each other, then that's an eclipsing binary, and that's a kind of variable star. There are, I mean, I could not, if I could start making a list of variable stars, and I would get 1/10 away before my memory is exhausted. There are so many different kinds of variables. Vega is a class of is a class of variable stars, actually. Very low amplitude, but still. Yeah, there's all sorts of different kinds.
Okay, so that's just one of them.
That's just one of them. Yes. Yes. Stars do not really behave themselves. Do you have a question?
Thank you. So as I understand, our sun transports energy through convection and then to the photosphere, and most of the energy goes out that way. You said when it went into the death branch that the convection went all the way out to near Earth's orbit.
That's because the star goes out to Earth's orbit.
So why isn't there like a photosphere? Where is the photosphere at that point? Is there still a photosphere at that point? Are we seeing something outside of Earth's orbit when we look at these?
It's still yes, it's still a photosphere, sort of, but I think that it's the idea that we have with the sun now we have a reasonably good boundary, and I think as these things get bigger and bigger, where you draw that boundary becomes a little bit more challenging. It's very wavelength dependent. The question you're asking is actually a really good one. Where's the boundary? Where does the star stop? And that's not actually a trivial question to answer. It gives the theorist fits. I'll put it that way. There's a question I think over here by the exit. We have to be quick because there's an exit involved.
Actually, this pertains to the slide you just had up there before, but when does oxygen start to show up in the scheme of things?
I think it went, oh, there we go. For a more massive AGB star, you could make some oxygen when you make the carbon. It's sort of like, just an extra helium atom in the middle of the process, and boom, there's an oxygen. So yeah, we get some of that, but it's for more massive stars. I think at solar metallicity on the other side of the carbon limit, so 5, 6, 7 solar masses, kind of a thing. There's another process there, and I didn't talk about, which astronomers, with their love for really bad names, it's called hot bottom burning, which involves protons getting captured. And what happens then is you actually you make carbon, but then you're converting it into nitrogen. This quickly gets, I'm not a nuclear fusion expert, and the more I keep talking on the subject, the more quickly you'll realize that. But yeah. Did that help though? Okay.
Okay, so we have a question from online asking, what are you most excited to learn about the sun from the Parker Solar Probe mission?
Is that the new one? That's the mission?
Yes, that's the new one. I don't know much about the Parker Solar Probe.
I don't know enough to answer the question, except that I know that the probe is going into like the corona.
Yep.
And that's going to be really impressive. I sort of am naturally curious about the solar wind because we're launching JWST, and there's this thing called space weathering, which is basically the result of sort of a steady cosmic ray bombardment. So what happens is over time, the detectors that we've launched will slowly be degraded by getting hit by cosmic rays. And the cosmic rays, which are really the problem, are the ones that come from the sun. So I'd be very curious. Anything we can learn more about that process, so we'd know when to take JWST and duck.
Okay.
So our sun has about 4 billion years left.
And change, yeah.
And change. Can anything catastrophic, unexpected occur that would derail that timeline?
For the sun?
Yeah.
Because anything, like humans might live to 80 or 90, but then things happen and some humans live to 30 or 40. Can the same happen? Can something unexpected occur?
The sun
with,
get into a car
the sun?
accident, huh?
Car accident. I was thinking of a stroke.
Live fast, die young, leave a good-looking
There
corpse.
is no process that I'm aware of. So I'm thinking probably not, but I've learned over the years to always hedge my bets ever so slightly. No, I don't. We've been studying these systems, like these globular clusters and stuff at different metallicity, and the stars are behaving more or less as we expect. There are certainly a lot of surprises, which is why we study them, but there's nothing grand on that scale. So I think we're okay. I think the real estate is safe for a bit.
I will say there was that one Star Trek film where the villain shot something into the star and made it explode. Yeah, we don't know about that. Other questions? Are we out of questions? One final question.
Oh yes, he's been trying to ask for quite a while.
I'm actually just kind of curious about the fusion reaction in a normal star like the sun. Does the fusion reaction begin in the center and move outward? And if that's true, how long does it take for the fusion reaction to get from the core of the sun to the surface?
Okay, so the fusion reaction is always just in the core. I think the number 20% by mass is in my head, but this is a fact check the speaker kind of a thing. So the idea is that the fusion reaction operates more efficiently in the center because the temperature is higher. But there's sort of a radius out to which the temperature is high enough to sustain some fusion, right? So what happens is, since the core is radiative, which means everything just sits there, there's no convection, the hydrogen gets exhausted faster in the center of the sun. So I think it's a pretty stable configuration for the last 4.7 billion years, by and large. But what's happening is that the amount of hydrogen in the core is going, in the center of the core is dropping fastest, and so it's slowly, the core is slowly gravitationally contracting, and the sun's heating up. If I remember right, the number is the sun is twice as bright now as it was when it first formed. When I was at Cornell, before I left, we inherited Lisa Kaltenegger and then her group, which is studying questions like the habitability of planets on other stars. They've been spending a lot of time looking into questions like this. Like, as the sun has evolved, the habitable zone in the solar system has moved outward, right? Because it's too hot. Venus may have been a habitable planet early in the system, or early in the history of the solar system, for example. There's other reasons it might not have been, because the atmosphere got pretty thick pretty quick. But, it's these kinds of things. Things aren't quite as static as we think of them being. It's a really neat question. And it gets even more intriguing when you start talking about exoplanetary systems, because now going, well, the habitable zone is between X and Y. Well, it's not that simple. So, yeah.
All right, we are getting to the end of our time. I have to cut off questions. We will see you again in September for 100 Ways to Die in the Universe. So, a little more death and destruction. Let us give one great big hand for Greg Sloan.
And thank y'all. That was a lot of fun. I appreciate that. I appreciate y'all coming out. That was fun.